Would you look at that? I am so sick of not solving equations that I caught a cold. How appropriate for the focus of our 9th class of Unit 7. Now, I genuinely apologize in advance if there are any sniffles or coughs or congestion or cleared throats in the background of this video. But I think it's about time, now that we know how to simplify and factor polynomial expressions, that we take those skills and use them to solve some polynomial equations. Okay, cool. We know how to break down polynomials into products of other polynomials, at least in theory. But why did we bother going through all that trouble of learning how to factor anyway? What does it do for us? Well, as it turns out, factoring is going to be our key, our linchpin to solving equations with polynomials. Given an equation, right, my goal is almost always to solve it. In other words, for something like x squared minus x equals 12, what is it exactly that I'm looking for in solving? 5 seconds, go. What am I looking for in solving an equation? 5, 4, 3, 2, 1. Well, the thing that I'm looking for, right, usually, I would call it a solution to my equation. A little math terminology for you. Sometimes, interchangeably with solution, you might also hear the word root of an equation. No matter whether I'm calling it a solution or a root, it does or should do the same thing to my equation. A solution or a root, by definition, right, we know that this is a value of the variable that we're working with, such that when I take it and substitute it back into my equation, it makes that equation true. So my goal, of course, is to make my equation true. But the process of solving polynomial equations is somehow a little bit more complicated than solving the linear equations that we're familiar with. The only question is why, and how can factoring help us? So let's take that first piece. What about polynomial equations makes solving them so difficult or so different? For example, x squared minus x equals 12. By trial and error, can you find a solution to this equation? And then if you've got one, tell me why you think the process of finding it might be a little bit weird. Go! Five, four, three, two, one. Let's chat. Well, the thing about polynomial equations, maybe when I asked you to find the solution, there was a little bit of a misnomer. Because unlike linear equations, where we have only one quote-unquote correct answer, for polynomials, more often than not, there is more than one value of the variable that makes this equation true. For this guy, x squared minus x equals 12, there are 2 correct answers to this question. Now, if you tried some positive numbers, you might have noticed that x could be 4, right? I could check that by doing some substitution. Well, if x is 4, then I have 4 squared minus 4 equals 12. 4 squared is 16. 16 minus 4 does indeed equal 12. But if you tried some negative numbers, you might have also puzzled out that negative 3 works for this equation as well, right? I could check my work here to make sure. Well, this is negative 3 squared minus negative 3 equals 12. Well, negative 3 squared means negative 3 times negative 3. That's equal to positive 9. Minus negative 3 becomes plus 3. 9 plus 3 also gets me to 12. What this tells me about the collection of correct answers, right? Or that there is a collection, right? Sometimes called, you may remember, the solution set of our equation, is that it contains more than one value. And I can write that value in set builder notation. Our notation for this, right, I would use my squiggly brackets just as normal. And if 4 and negative 3 are in my solution set, by convention, right, I'd probably put the negative 3 before the 4 because the negative 3 is smaller than the 4. And I like to order in math from least to greatest. Cool. So I know now that polynomial equations often have multiple solutions. The question that remains for us then is, well, how is factoring going to help us find them? In math, there are lots of numbers that are really powerful and have lots of applications. It turns out that 0 is one of those numbers. And this friend, the 0 property, will in fact be our saving grace in the process of solving our polynomial equations. I've started it out here for you. The zero property says that the product of two or more factors is zero if and only if some criteria is met. What criteria would need to be true? I'm multiplying a bunch of things together and I get zero. What does that tell you about the things being multiplied? And how do you think that applies to solving our polynomial equations? Take a risk, take a chance, be wrong, who cares? What do you think the completed zero property says? And how do you think I can apply it to a polynomial equation like this one? Go! Alrighty. Well, logically, if I'm taking a bunch of things, multiplying them together, and getting zero, the only way that can be true is if at least one of the things that I multiplied was zero. So in other words, right, one of those factors must be zero if when I'm multiplying all of them together, I get zero. And what that should hopefully tell me about polynomial equations is that if I can break my polynomial into factors, if I know that the polynomial equals zero, what that should tell me is that one of the factors of the polynomial must be zero as well. Cool. So, with this logic in mind, I'm going to take x squared minus x equals 12. In order to use the zero property, I need to get a zero somewhere. So what opening move do you think I might make? 10 seconds, go. 5, 4, 3, 2, 1. Did I say 10 seconds? I lied, I'm too anxious. I said I was sick of not solving polynomial equations. X squared minus x equals 12. I need to get a zero somewhere to use a zero property. Well, the easiest move I could make would be to subtract 12 from both sides. Making this choice, x squared minus x, right? I'm going to put my minus 12 at the back, keep it in standard form, is equal to 0. Now I know this whole polynomial is equal to 0. So if I can factor it, that means one of the factors must be 0 so that when I multiply back out, I get back to 0. Well, can you take a couple seconds? Can you factor x squared minus x minus 12 for me? And once you've got it, how do you think I can use this zero property to my advantage? Go. And stop. X squared minus x minus 12 equals 0. Well, x squared minus x minus 12, this is a quadratic trinomial. I know that its factors are always going to be two linear binomials. At the front, it's got to be x times x to get to x squared. At the back, I need two numbers that multiply to negative 12 and add to negative x. Well, that should be negative 4 and positive 3. Now by the zero property, what this tells me is that if x minus 4 times x plus 3 is equal to 0, then one of these must be 0. So either by the zero property, the x minus 4 is 0, or by the zero property, the x plus 3 is equal to 0. All I need to do now is solve for x. Well, if I have x minus 4 equals 0, let me add 4 to both sides. Here I find that x equals 4. If I have x plus 3 equals 0, subtracting 3 from both sides tells me that x is equal to negative 3. And would you look at that, this solution set, negative 3, 4, is exactly the same solution set that we found up above. Cool. So there's the idea, right? As long as I can get a 0 on one side and a bunch of factors on the other, I can take each factor, set each one to 0 individually, and find the value of the variable that makes that factor 0 as I would any linear equation. Cool. Now, when I'm working with different types of polynomial equations, they can come in a bunch of different shapes and sizes. Sometimes, if we're really lucky, our polynomials will already be factored for us. For example, take each of these guys. 2y times the quantity y minus 4 equals 0. 0 equals the quantity 5p minus 6, p plus 3. Or 7z times the quantity z minus 1 squared is equal to 0. By the zero property, right, what should I do with each of these factors? Can you find the values of the variables for me? Take a minute, play around, see what you get. Go! And stop. Let's do it. I'm anxious. So I have 2y times y minus 4. By the zero property, what this tells me is if the product of 2y and y minus 4 is equal to 0, then either 2y has to be 0 or y minus 4 has to be equal to 0. All I need to do now is solve for my variable. Well, here I'm going to divide both sides by 2 to get y by itself. Y could be 0. Or if y minus 4 is equal to 0, I can add 4 to both sides. Here, y would be 4. In set builder notation, that tells me here that my solution set contains the values 0 and 4. For my second one, 0 equals 5p minus 6 times p plus 3. Well, by the zero property, once again, if the product is 0, then one of the factors must be 0. So either the 5p minus 6 could be our 0, or the p plus 3 could be our 0. If 5p minus 6 is 0, well, I need to get p by itself. Let me start by adding 6 to both sides. 5p here would be equal to 6, dividing both sides by 5 to isolate my variable. Here, p would be equal to 6/5. Or if p plus 3 is 0, to get p by itself, all I need to do is subtract 3 from both sides. Here, p could be -3. Right, so in my set builder notation, my solution set contains the values of -3 and 6/5 for p. And for my last one, 7z times the quantity z minus 1 squared equals 0. Well, I know what z minus 1 squared is, right? That's z minus 1 times z minus 1. By my zero property, now any of these three could have been the 0. So either by the zero property, the 7z could be the 0, maybe the z minus 1 in the middle was the 0, or maybe the z minus 1 at the back was 0. Once again, right, I'm going to solve for z in each of my equations. Dividing by 7, I could say that z is equal to 0. That's one of my options. Or if z minus 1 equals 0, right, adding 1 to both sides in both of these equations should show me that z is equal to +1. But look at your solution set here. Notice that 1 shows up twice. That's a little wonky. We have a fancy name for this guy in math. A solution that appears multiple times we call a multiple root, right? Root being an interchangeable word for solution. So this guy we are going to call a double root of our equation. Sometimes double root is abbreviated as dr, right? This just means this value shows up twice in the solutions to our factors. But when I'm writing it in set builder notation, right, I'd still just put 0 and 1, right? I don't need to do double duty with that 1, but underneath it, right, I might do something like times 2 or double root just to indicate that this 1 is in fact a double root of my equation. Let me give you 2 more to solve. Using this idea, I want to find my solution set for each of the following equations. Go ahead. Five, four, three, two, 1, and stop. Well, here, notice that in both of my equations, right, I'm already fully factored. So I have 2g plus 1, which by the zero property could be my 0. I have 3g minus 4, which by my zero property, that could be my 0. Or the g plus 7 at the back, that could be my 0 as well. I need to solve for g in each of these equations. Well, let me start with the 1 on the left. Subtracting 1 from both sides, 2g is equal to -1. Dividing both sides by 2, I find that g is equal to -1/2. So here's my first possible value of g. For my second, I'm going to start by adding 4 to both sides. So this gives me 3g is equal to +4. Dividing both sides by 3, The second value of g that it could be is 4/3. And last but not least, if g plus 7 is 0, well, I could subtract 7 from both sides. Here, g could be equal to -7. If I so choose, I could use my solution set notation in set builder notation to write it. Well, -7 is the smallest of my three, so it's going to go first, followed by the -1/2, that's the second smallest, and then finally 4/3 is my biggest at the back. And I've got this guy over here, 0 equals 4d, 3d minus 2 squared, d plus 6, and 5d plus 8. Again, by my 0 property. Any of these factors could be my 0. So either my 4d gives me 0, either my 3d minus 2 gives me 0, either my d plus 6 gives me 0, or my 5d plus 8 gives me 0. Well, if 4d is equal to 0, dividing both sides by 4, here d would have to be equal to 0. If 3d minus 2 is equal to 0, well, let me start by adding 2 to both sides. Then I could show that 3d is equal to 2. Dividing both sides by 3 to isolate our d, here d could be 2/3. For our third, right, d plus 6 is equal to 0, so I'm going to subtract 6 from both sides. Here d is equal to -6. And last but not least, right, if I subtract 8 from both sides in my equation all the way on the right, 5d could be equal to -8. Dividing both sides by 5 to isolate my variable, in that last equation, my final value of d, it could be -8/5. The only thing that I'm going to do here that I have not yet done, well, notice that this 3d minus 2, that factor showed up twice in the equation, so that tells me that this guy is going to need to be a double root, right? The factor shows up twice, therefore the solution shows up twice. And if I really wanted to, I could also write this solution set in my set builder notation. Well, of my values, the smallest is -6, so that goes first, followed by the -8/5, followed by the 0, followed by the 2/3. Now, we said that sometimes we will be in factored form, but sometimes we won't. So n squared minus 81 equals 0. -6x equals x squared plus 9. These two problems will be where we start together next time. But until then, I want you to think a little bit about how you'd go about solving these, right? We know we might need to factor on our own if we're not so lucky to have them given to us. If you're feeling bold, try and solve them yourself. Maybe you'll come into class with the questions already answered.